Okay. As a review, for this chapter 4, to begin our course, I will start with the last time we discussed the sketching the graph. Okay. So the idea for sketching the graph is first, okay, the basic idea is just to know the domain. Okay. First is to know the domain. I think intercept is not too important, but if you wanted to make sure to confirm at y0 and or x0, you can also check the intercept. And then I want to point out the asymptote. Okay, so asymptote, you can have horizontal or vertical, like we have done before, right? So you have horizontal asymptote, which defined by the limit as x approaching infinity. Okay. So of course, if it's equal to some value here, then this 0 or y equals 0 is horizontal asymptote. Okay, and then this 0 and 1 for the limit. Okay, 0 and 1 is you get the 0 and 1 from the domain. Okay, because in the terms of the functions, you cannot have x0 and you cannot have x is equal 1. Okay, because when you are putting 0 or 1, you are making the functions become undefined. Okay, so that's why I'm trying to guess the 0 and 1 and check whether they are really become infinite or negative infinity. And how to check the limit. Okay, and remember, okay, all the concepts like from the beginning of the course, like the limit, how to derive, and so on and so forth, differentiable, continuous functions, all the concept will be remain, and you will need it until next year. Okay, until next year. So Cal 1, we are basically deriving the first part on our whole lecture this semester is all differentiations. Okay, and we need the tools for differentiations, limit. Okay, and then the next part, the second half, will be integration, in which you can see the integration as if you derive something. For example, x squared, you derive to 2x. Integrations mean you are thinking backwards and find the antiderivative. But we can also use the integrations to check the area under the curve, in which maybe, if not today, maybe next Thursday, I will start the integration. But before that, going back to limit, okay, if you need to check limit at some point here, you can check from the left side or right side, okay? And that's why you can get, maybe this is positive, maybe negative. It depends on how the function is moving, okay? You can check 0, 0 0.1, 0 0.5, okay? Or maybe in the negative one, negative 0.1, okay? You can check and see how the graphs will move, okay? And you will get the vertical asymptote. So again, GPrime test. Why you need the GPrime test? First, you can get critical point. The second, you can get the idea where the functions will be increasing or decreasing. Okay, that's the first derivative test. Okay, to check if it is equal 0, then the x inside this GPrime will be your critical point. Usually, okay, usually your critical point will be your max or minimum. Usually, but not always the case. Okay. Okay, and then after we dealing with the GPrime, can check the GPrime. If we do not have any critical point, we can check at least the number around the asymptote, the vertical asymptote, 0 and 1. Okay, you can check how the function will increase or not. Okay, and you can check from here is actually the functions or the derivative. If you check you want to solve for x, you can check with the determinant, the quadratic formula, it's being negative inside this square root, right? So that's mean there is no real solution. The roots for this function will be imaginary. So it's not applicable in our conditions, but but we still can get the idea when the function is increasing or decreasing. Okay, despite the fact that there is no critical point here. Okay, so after G prime, we check the second derivative. Okay, second derivative. The idea for second derivative is to test whether the function is upwards or downwards. Okay, just the how the curve looks like. Okay? And we get the idea here. We solve this. Um, this is actually not really a calculus thing. This is how to solve in polynomial. Uh, you can check through, if you want, you can check through, this is called the Descartes rule for highest degree of polynomial. Okay? You can check how the signs changing in positive x and in negative x also. You can see there's no change in sign. You can plug in into a table to see our possibility of roots. Okay, so the first possibility is we have three positive number, and its total is 3 because it's cubic, should be 3 in total, or we can have one positive, and the other two will be imaginary. Okay? And how to check? We can check using division, synthetic division, and actually, if you have polynomial, okay, usually the last part and the first part, if you divide the last and the first part, you will get the possible of roots. So the factor of 1 is only plus minus 1. There's nothing else there for integer. Okay, this is applicable for integers only. Okay, and factor 4, you can have 1, 2, 4. Okay, so 1 multiplied by 4 is 4. 2, 2, 4. Right. So it's factor of 4. And possible fruits, you can divide 1 divided by 1 is 1, 1 divided by 2, half, 1 divided by 4, 1/4. So if you have more than, like, maybe it's 6 or maybe it's 8, then this should be factor of 6 or factor of 8. And then you need to divide with the first term. Okay? And then checking all this number. But because we only have the positive number here, the possibility, okay, either 3 or 1, we can check the positive one only. Check 1. Maybe you are not getting 0 here, but we get 0 at half. Okay, we get 0 at half because this is all the second derivative. Okay, second derivative. So when second derivative equal 0, meaning this x will be our inflection point. Okay, that's our predictions. Actually, we can also checking the this half. Okay, I'm putting inside the vertical asymptote, and in between there will be inflection point, and how our graphs looks like. Okay, so because we already decided at 0 we will going to have positive infinity. So from below going up, and it will be infinitely larger, right? But here in between it's half. Okay, you will get upwards, but it's decreasing. Okay, from the first derivative, it's decreasing, and then change the concavity as half, and then downwards. Okay, and then here it will be downwards, but it's going to negative infinity, so it's going down. Okay, okay, so we conclude that this is our graph. Okay, and we can actually draw the graph through calculus. Okay? And this is with the calculator graphs. Okay, it's not too noticeable the half here, but it's actually, if you zoom in, you will see a slight inflection, Okay, and now because we now have deal with the vertical asymptote, the horizontal asymptote. Okay, now I want to add another asymptote. It's called the slant asymptote. So it's not vertical, it's not horizontal, but it's linear equations. Okay? It's linear equations. They make more closer to the functions. Okay. So the blue color will be our functions fx. Okay. And our red color here, the red line, I will note this as our mx plus b. Okay. Just a linear equation. Just a linear equation. Okay. So the definitions of the slant asymptote. Okay. So the slant asymptote is any linear equations that is not vertical, not horizontal. And when you are having a function, the functions will not crossing this line. Okay. Let's say we have a gap here. Okay. A gap between the functions and the linear equations. Okay. The definitions of the slant asymptote, okay, based on a limit. Okay. So as the x approaching infinity, okay, as x going forwards, the difference between the functions and the linear equations is equal 0. Okay, so this is the definition for slant asymptote. And then how to find the slant asymptote? Okay, the slant asymptote usually will be it will appear because of the rational functions, or let me write rational. Okay, so if I have any polynomial defined by polynomials less 1 degree, 1 degree less than the numerator. For example, maybe x squared plus 3x minus 2. And then this is x squared minus 1. Okay. Of course, if you divide, at least you will receive linear equations. At least you need to multiply by x to get the cube, right? And you can rewrite this with another form that has the linear equations. Okay. If you remember the polynomial, let me use a good function. This is just a makeup function. I'm not sure what this looks like. Let's just having hx. Okay. Let's start with the quadratic. Okay. Okay. To solve this, I think because this is simple functions, you can just define uh, easily by polynomial efficiency. Okay. You can divide x squared minus x and then minus. This will be 2x minus 1, right? And you have now 2x plus 2, 2x minus 2 plus 1, right? So meaning this is your remainder. Okay, remainder. It's called the remainder. If this is 0, if this is resulting 0, then this x minus 1 is the factor of this function. Okay. If not, then this is remainder. Okay. So it's called the remainder. Let's write just r remainder. Okay. So I can rewrite the h of x plus 2 plus the remainder and the diffuser. Okay. Okay. So you can write the linear equations plus the remainder over the diffuser, okay, x minus 1. So in this case, this x plus 2 is our slant asymptote. And if the polynomial getting complicated, you can also use this. Uh, I think you remember this. So divide through the I call this the synthetic division, but I think you're already familiar with it. So this become one multiply here, okay? So 1, and then 2, it's plus, okay? And then 2, it's 1. Same results. This is the remainder. This is the x plus 2. And this is what the graphs looks like. So the red line will be the x plus 2. Okay? So you will see that it has a gap, right? It has a gap that when you are approaching x forwards to infinity, the gap becoming closer and closer, right? It's becoming 0. Okay, not exactly 0, but limit 0. Okay, you get what I mean? Okay, limit in limit. Okay, so that's all this slant asymptote. But it's just the additional notes for sketching the graph that you can also find the slant asymptote. Okay. The next section will be the optimizations. I think in your textbook, it should be on chapter 4.7. But let me write optimization. I believe for optimizations, uh, I think you've learned. So if you have learned the functions, the derivative of the functions in high school, you should. I think you should learn this optimization. So usually it's similar with finding the critical point, and then with the critical point we are using it for maximum or minimum value. Same, right? Okay. So the idea, okay, uh, you will have a case, okay, a problem related to a critical point. So to solve the problem, usually you need to draw a diagram. And then naming the variable. It's basically the first part of the sections. It's similar to the related rates. Okay? You see the problem, maybe you draw, okay? Like in your quiz, you draw the lighthouse, blah, 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 right? And then naming the variables. You can name anything, A, B, X, Y, okay? Naming variables. Okay? And then find relations or formula, okay? Or models. And then find the max or minimum value through the f prime x equals 0. So this is pretty much summary of this optimization. Okay, so you will have a problem, okay, like you have a box with certain area, and you want to make the from that area you want to make the volume as maximum as possible or as minimum as possible, and check the diagram, check the variables, okay. And also for these relations, I will make some notes here. There will be a constraint. We call this is constraint equations, and we have optimizations. So at least, okay, at least in your problem, there will be two formulas, at least. Okay. Constraint, in which they will have a fixed, a constant that you need to have inside the optimization. And you have optimization. The one that you need to derive is the optimization. Okay. Like you need to find the minimum area. Then you have the area. You need to derive the area with the constraint from the other equations that you find in the questions. Okay. Let me give you the um, let me give you the example, the obvious example for the optimizations. Let me write here example. Okay, I will give you example and what does it mean in another terms. Okay, if okay, so you have, okay, first is the area, right? 1,200. And then you want to make a box with a squared base. Okay, so you have a box. The base is squared, okay, but without any top. Okay, so this is the obvious question, and after this question, I will also tell you the another possibility for the question. It's a box, an open top. Okay, so maybe you can draw the diagram. Let's just say the square at the bottom is x, okay, and maybe the other variable will be y, and this top is nothing. Okay, so if you have 1,200, it means this side plus this side plus this side for this side, 4xy plus x squared, right? And this is whole here, right? For the 1,200. Okay. This is the surface, right? The area. So let me write x squared plus 4xy is 1,200. Okay. So I will remind you again, this is our constraint. What constraint means here, it will limit our calculation based on this information. Okay. And the other part is because we need to find the largest possible, not value, sorry, should be volume. So volume will be x squared y, right? X squared y. And this is we call the optimization. Okay. Like I like I've write before that if you want to optimize, you need to derive and equaling to 0 to check the critical point. Okay. But here we have volume, the one that we need to find, the functions, right? This is the models that you want to find. But you have now two variables here, okay? X squared and then y. You have x and y here. Okay, because we have the constraint here, we can rewrite the form and try to find the relations in x and y and then substitute to here. So there will be only one variable and it will be easier to for calculation. Okay? So let's do that. Let me move to the next page. Okay. So let me write for xy. Okay. Divide by 4x will be 300 over x, right? d5 x 4. Okay. So this is our y here. And we can write the volume x squared and we can simplify okay. This is our models. Okay. So this is so the idea is to derive this. So let's derive and become v prime. So just derive with the respect to x. Okay. So 300 okay, and then make it 0 to find our critical point. And then x squared is 400. Then x will be, it should be plus minus 20, but because we are dealing with the real problem, we can ignore the negative. Okay. So x, choose positive. And y will be 300 over 20 minus 20 over 4. 15, 5, 10, right? So our volume will be 20 squared 10. It's centimeter cube. Okay, that's the first example, an obvious example. I will give you another example, similar, but let's see. Another example, wire length 1 meter, cut into 2 pieces. Each piece encloses a square. Find the largest area encloses. Okay, let me tell you what is this. Okay, so you have a wire. Okay, you have a wire. with 1 meter's length. Okay, it cut and become two wire, and from two wire you are making a square. So you have a two square. Okay, what you need to find is you have the area of the square, right? You need to find the largest area possible, the largest area. See if you can get the idea why this question is actually a little bit different from before. The idea is still the same. Okay, you draw the diagram, maybe the wire, and cut and make one of them variables like x, and the other one will be 1 minus x, and then make some square, find the formula. It seems. Let me draw for you. Cut here. So if this is x, this is 1 minus x. So this will be, if this is square, these sides will be x over 4, right? And the other one will be maybe bigger. So we draw the diagram, naming the variables, and then write down the equations. So equations, we get x squared. Let me write just x to the 4 with divided by 4, and then squared, right? And then plus. Okay, so this is our equation from these two areas. Okay, we combine becomes 2. Okay, um, let me write this is a. Okay, this is a. Okay, and let me derive these models. Okay, because our intuition say that we need to check the derivative and make it 0, find critical point, right? Like the previous slide. Let's check the first derivative. So it will be x over 8, right? Because 2 and 16, right? Yeah. And then should be minus. Same. Let me rewrite this 2x minus 1. Okay. It seems that we have this conclusion. So x will be half, right? It seems this is our critical point, right? And then let's just take our critical point and put in our functions. So it will be 1 over 8. And then half, 1 minus half is half, half, uh, the same. So it should be 1 over 64, 1 over 64. So it will be 1 over 32, right? And then maybe in the exam, you write, okay, this is the largest, the max value. Okay. Until here, you get it? Okay. This is actually really, really problematic, actually. Okay. So we conclude that this is our max. Okay? This is our max. Let me write here. Okay. Is 1 over 3 maximum value? Okay. Do you agree this is maximum value, 1 over 32? Okay. Okay. This is sometimes, okay. Uh, Students uh, in math, okay, calculus or any mathematical problems, okay, they usually try to learn the math or calculus chapter by chapter. Okay, chapter 1. Okay, chapter 2, chapter 3. They usually forgetting that the whole calculus or whole math is actually integrated as one. If this is only appear at the chapter of optimizations, I can tolerate that. Okay, maybe 1 over 32. Okay, but okay, if we check this 1 over 32, let's go back to our critical point is half. Okay, let's check this one. Let's just say that this is your point, and what you did previously in checking the f prime, right? F prime test, right? Now, what is your endpoint? Your wire is 1 meter length, right? So let's say our endpoint 0 to 1. Okay, let's say that this is 0 to 1. Okay, what is happening here? Check some point. Uh, this is the f prime. If you are putting something maybe around here, maybe 1 over 4, it's minus, right? It's minus. Agree? Minus. Okay. Check somewhere in between here, maybe 2/3. 2/3 is positive, right? Positive, right? And what happened to your graph? The gradient going down and then going up, right? So this is your graph. So this half is minimum. Okay. So what I want to learn is the chapter 4. The whole concept of chapter 4 is basically in the summary for the sketching graph. That's the whole thing of chapter 4. So this is actually part of the finding max and min, right? So if I gave the questions like that, then most of you will be getting wrong answer, right? So the answer will be, you can imagine the limit, okay? So going to 0 from right, or going to 1 from left, okay? You can check the limit value. So limit as x approaching 0 from the right of your fx. And also you can use the other. Okay. So let's just check our. So if x is 0, so let's just substitute 0 here. So it's become 0. It becomes 1 over 4 squared. It becomes 1 over 16. But that's actually because if you have 0, so your wire is just gone, right? So let's just say to make this logical, this is the limit, okay? Limit. So a little bit okay, right? So this become 1 over 16. And the other part, we have the x equal 1. This becomes 0. This becomes 1 over 16. Okay. So the largest maximum is actually this 1 over 16. We get this from the endpoint. Okay. Remember that when you have the interval, you have functions, you have interval, you need to check the critical point and also the endpoint. And also the endpoint. And this is the endpoint. The 1 and 0 is your endpoint. Okay. But uh, luckily, in your textbook, the question is always correct. Okay, so you don't need to be worried. Max, min. Okay, but in case, okay, in case something is wrong, then maybe the question is wrong. Maybe the question is wrong. Okay, I haven't checked all the questions, but most the questions has in the textbook, they always have the right question. So if they say the minimum, and yeah, it means it will be like the curve will be going down. Okay, it will not be like this. Okay, this is like to check whether you understand the chapter 4 or not. Okay, so the answer is actually this 1 over 16 in limit value. Okay, because if not using limit, then it's impossible. If your x is 0, your wire is gone, right? You lose your wire. Okay. So this is 1 over 32 is minimum value. Okay, any questions? Okay, let me move on. Um, this is another example. Let me move on and give you another example. Okay, maybe this example. Okay, find a box without a top. I think it's quite similar to the first one. With least surface area for a fixed volume. And the box will be, the box is squared bottom. And now the questions is corrected. Okay? Uh, let me read the questions. Okay, find a box without a top. Okay, with least surface area. So your area will be your optimizations, and it will be asking the minimum. Okay, the least surface. Okay, for a fixed volume. So fixed volume means the volume becomes a constant. Okay, so sometimes it doesn't always have the number, but it will tell you which one is a constant. So that means you treat the V, the volume, like a number, like a constant. Okay, so when you derive, it will be 0. Okay. Let x, y. I think this is pretty similar, but the difference is the volume now become the constraint because it has the constant. And the area, x squared plus 4xy, this become the optimization. Okay. And solve from the constraint. Somehow you rewrite the form and put y. I think the easiest one is y to change here. So you'll get the y is volume over x squared, and then change all the equations for v over x. Okay, so this is your models, your optimization equations. Okay? So it's all one variables. Okay, the phi is the constant. Okay, so we can derive. So a prime will become 2x minus 4v over x. And let's equal this equation to 0. So we get let's say this is the x cubed. So x cubed will be 2p. So x will be so you need to have your box with x is equal to a square root of the cube root of 2p. In case you want to make sure that this is correct. Okay, let's check the 2p. Okay. How to check? How to make the endpoint? Let's say it doesn't have any limitation on x. Let's say you start from 0 to infinity. Okay. You can use the a prime, checking this one and checking the region in between here. But because we don't have the really good number, I think we can check the limit with this one. Okay. So checking limit, first checking limit. As x getting positive. Let's say this is a, okay, and then checking limit as x getting negative, but from the left. Okay, see here. Okay, if you approaching 0 from the right, it will have over x here, right? Which means you will have an infinite number, right? So you will have infinite. If you have infinite from the left, you have infinite, but you will have 0 here. So probably this will be looks like, so going here will be infinity, going here will be infinity. And that's true if you want to make sure that this is our minimum value. Okay. So from previous one, this is the question already corrected. It's asking the minimum instead of the largest possible. You can also, instead using the A prime, you can also use the second derivative. Okay. Why we need second derivative? If you want to check the concave upwards or downwards, it's also can be used. So let's write the double prime. 2, it will be a plus 8vx cubed. So let's check x is, if we put the x equal this, our results, put here, it will be 2v is is uh, it's positive number, right? It's positive number. So because it's positive number, what can you conclude from here? It's concave upwards, or it's like this. And then you can also conclude that it will be minimum value here. Okay? You can you can do pretty much just f prime test. That's fine. You want to make sure with double prime, you can do it also. Okay? So in whole chapter 4, the idea of the sketching the graph is really basic throughout all the theory in chapter 4. The maximum minimum theorem, the second derivative, the optimizations, all based on uh, how to sketch a graph. Okay. And sometimes the question is not always finding the exact like x equal what. Okay. You can also have a questions asking the maybe the ratio between x over y. Okay. The question may ask the ratio. So you need to look back at y and then substitute and find the ratio. If you substitute, this will be 2 over 1. Okay, so x need to be twice bigger than 1. Okay, let me give you another example. And now I think the question already corrected, so you don't need to worry to checking the maximum minimum. Okay, now cylinder. Okay, cylinder. Okay, cylinder. Let me draw the cylinder. Okay, cylinder. Okay, remember the volume of cylinder? What is volume for cylinder? What is the volume for cylinder? Remember? Usually all three-dimensional object usually start from the area of the base times height, right? It's always the case, right? If you have a trapezoidal, rectangular, it's always the area of the base times height. Let me write this is let me write this R and H. So my volume will be 4 because the volume is fixed volume, then I will say this is my constraint. And what is the surface area of the cylinder? The area. You need to add the circle. There is two circles, right? And this hold the middle thing, right? This pi r squared, so 2 pi r squared, right? Plus, what is this surface area of this? 2 pi r h, right? Okay. Do you know how to get it? No, right? Okay. So imagine if you cut, remove the circle, it will be a rectangle, right? In case you're wondering, so it will be a rectangle. Okay. This will be the height. This length will be the circumference of the circle, right? Which is the 2 pi r. Okay. That's why this area will be 2 pi r h. Okay. So this 2 pi r h. And let me write this as the optimization. Okay, it's asking. Let me write asking the r over h when SA minimum, the surface area minimum. Now, and again in optimization, you will have this kind of problem. You have the radius and you have height, right? And we need the same method to change the height at least to make it all in r, right? But instead of that, I will make, because we have volume is PR squared h, okay? Let me divide this become V over R, okay? This will be PRH, okay? So instead substituting H, I will substituting V over R for PRH, okay? Okay. So my surface area will be 2 pi R squared plus, so PRH, so 2 PRH. So 2 PR, okay? So I'm removing the PRH and change to V over R. So it's all in one variable R. The volume is constant. And I can minimize the surface area. If you want to make the symbols with anything you like, A, B, S, A, Z, anything. Um, it's not a problem. It's not a big problem. But always remember this your model, and you derive your model. And minus, and let this equation equal 0. So this will be r cube and then change back to so you get the r over h, or r is h over 2. R over h is okay. One note that um, I need to mention, uh, minimizing or maximizing the problem. Usually, if you get like the models like this one, it's easy to derive, right? It's not too difficult, okay? But what if, okay? If your models is like a distance, okay? For example, the distance is maybe x minus 2 plus y plus 8, okay? And you need to make this minimum or maximum. You have the square, right? The idea for the whole thing in optimizations is this is only a model. So because of that, I can just make sure that I count the inside, just inside, like this one. So I'm just making another model in which if I make this minimum, this also minimum, right? It's the same thing. And you will get the critical point no matter what. So you can simplify your models. If you think your relations or your formula is too complicated, you can minimize or you can simplify the formula. Okay? Unless if you want to derive the whole thing, that's fine. But if you want to make faster, you can ignore the square root, okay, and just maximizing or minimizing the inside. This is just a make-up functions, okay. 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 I think last example. Okay, consider triangles formed by lines passing through point um, find dimensions that minimize the area. Meaning the area of the uh, triangle. Okay, so you have x-axis, y-axis, and you have a line passing through 8 and 4. Okay? And the optimizations will be the area of the triangle. Okay? And you have 8, 4, that should be your constraint. So at least there will be, I think, at least three variables to check. Okay? Either x, y, or the other variable that might appear, the gradient, because we don't really know the gradient, right? Can you try this one and check whether you get the idea or not? And if you finish, let me know. I will give you maybe around maybe seven minutes to check. 6 to 7 minutes. Let me draw to help you get the idea of the questions. Let's say this is x, y. Maybe here is we have this triangle, and you need to minimize this triangle. Yeah, you can just use x, y, so half x, y is your triangle. Minimize that. Triangle. Yeah. Oh. Yeah. You have Peter? You have Peter? Okay. No problem. The idea, use the line equation. 16, right? 16. Yeah. And y is what? Get y? 4, 4, 8, right? 8, yeah. So using the x, right? What is x and y? X, 16 and 8, right? And how you find using the gradient is negative half. Okay. Um, we can write the line equations. Okay. Y minus 4 is, let's say, the gradient, and then x minus 8. And we can get easily this x and y if we just making the intercept y0 and x0. Okay. So when y is 0, it will be minus 4 mx minus 8m. Let me solve for x, and also when x is 0. So y is 4. Okay. Now, let's say this is your constraint, and your area is half xy. Let's say this is your optimization. So I've seen some your works. Some of you using the x, but I'm using the m as my variables. Okay. So a will be half. Let's divide 2. This become 2 minus 4. So a will be, let me rewrite all the 16, 52m. Okay, so this is my area. Now, as I mentioned before, we can simplify our models. Okay, I will multiply all with the m. Okay, so let me write this as a new model B. Okay, in which I multiply by m. So I will get and then make this 0. And the m should be half. Okay? But because of our gradient is going down, so we'll have negative half. So x will be 8 minus 4, this negative half, 16, and y will be form it's 8. So area will be 64. But actually, the questions is, I believe this is not really in. It's really obvious, okay? Because 8, 4, you can get the gradient easily, right? 4, 8 is half, right? So you can get the easily the m is negative 4 over 8. It's negative, right? Because usually you have this y over x, right? And because it's going down here, it's negative 4. Yeah. Actually, it's quite obvious. You get the answer directly from here. Okay? But this is, I just want to show you that we can also make some models like this. Okay. Okay. Any questions? If not, then I think we can finish until here. Okay. Because after this section should be the new chapter. I believe it's better if we just make it on Thursday. Okay. Because we only have a little bit time now. So okay. And again, okay, I previously I didn't mention in the other class about how I get this. I multiply with m. Okay, this is practically I'm using another model that it's aligned with previous model, and you can do that also. So if you see like the square root or anything that you find difficult to derive, maybe you can simplify your equations as long as you get the minimum or the maximum for the critical point. As long as you get that and it's logical in the questions, then you can simplify the equations inside. Okay. Okay. So optimizations. First, draw diagram naming variables similar to related rates. Find the relations, formula, constraint equation, optimization equations. Find the first derivative, make equal 0, and that's your critical point. And check your critical point, and that's your mix, your max value or min value. That's it. Okay. To learn more or to practice more, you need to see the case, the problem. Okay. Okay. And yeah, next Thursday I will also deliver you your quiz. I think there's one student get 100. Yeah. Some getting 90 something. Some also get below 50 or 40. Okay. Okay. Okay, I think that's all for today.